When dealing with a 240 to 120 volt 15 kVA transformer that has only zone and X4 secondary connections, it is essential to understand the grounding requirements. According to electrical codes and best practices, either zone or X4 should be grounded to a grounding electrode system. Grounding is a critical safety measure in electrical systems for several key reasons. Firstly, it provides a low impedance path for fault currents to return to the source. This low impedance path facilitates the rapid operation of overcurrent protection devices such as circuit breakers or fuses during a ground fault. Without proper grounding, a ground fault could result in elevated voltage levels on exposed conductive surfaces, posing a significant shock hazard. Secondly, grounding helps to stabilize the voltage to ground during normal operation. In an ungrounded system, the voltage to ground can fluctuate, which can stress insulation and lead to equipment failure over time. Grounding provides a reference point, ensuring that the voltage to ground remains relatively stable. Thirdly, grounding minimizes the risk of static electricity buildup. Static electricity can accumulate on equipment and structures, especially in dry environments. A properly grounded system dissipates static charges, reducing the risk of sparks and potential ignition of flammable materials. The grounding electrode system typically consists of one or more grounding electrodes that are bonded together to form a common grounding point. Common types of grounding electrodes include ground rods, ground plates, and metal underground water pipes. The grounding electrode system should have a resistance to ground that meets the requirements of the applicable electrical codes, such as the National Electrical Code, or NEC. The NEC specifies the requirements for grounding and bonding electrical systems, including transformers. Section 250.30 of the NEC covers the grounding of separately derived systems, which includes transformers. This section requires that the secondary winding of a transformer be grounded if the system voltage exceeds 150 volts to ground, or if the system is a three-phase, four-wire system. In the case of a 240 to 120 volt transformer, the secondary voltage is 120 volts to ground, which is less than 150 volts. However, the NEC still requires that the secondary be grounded to provide a low impedance path for fault currents and to stabilize the voltage to ground. The specific point on the secondary winding that is grounded depends on the transformer connection. For a 240 to 120 volt transformer with only zone and X4 secondary connections, either zone or X4 can be grounded. Grounding zone will result in a neutral conductor that is referenced to ground, while grounding X4 will result in a different phase conductor being referenced to ground. The choice of which point to ground depends on the specific application and the desired system configuration. When grounding the transformer, it is important to use the correct size grounding conductor. The size of the grounding conductor is determined by the size of the transformer's secondary conductors. NEC Table 250.102. C1 provides guidance on the minimum size of grounding conductors for transformers. The grounding conductor should be connected to the grounding electrode system using approved methods such as exothermic welding or listed grounding connectors. It is also important to ensure that all metal enclosures and equipment associated with the transformer are properly bonded to the grounding system. Bonding is the process of connecting all metal parts together to create a low impedance path for fault currents. This includes the transformer enclosure, conduit, and any other metal equipment that could become energized during a fault. NEC Section 250.92 specifies the requirements for bonding metal enclosures and equipment. In addition to grounding and bonding, it is also important to provide overcurrent protection for the transformer. Overcurrent protection devices, such as circuit breakers or fuses, are designed to protect the transformer from overload and short-circuit conditions. The size of the overcurrent protection device should be based on the transformer's kVA rating and the secondary voltage. NEC Table 450.3. It provides guidance on the maximum size of overcurrent protection devices for transformers. When installing a transformer, it is important to follow all applicable electrical codes and standards. This includes obtaining the necessary permits, performing a thorough inspection, and testing the installation to ensure that it is safe and compliant. It is also important to consult with a qualified electrical engineer or electrician to ensure that the installation is properly designed and installed. Proper grounding of a 240 to 120 volt transformer is essential for safety and reliability. By following the requirements of the NEC and best practices, you can ensure that the transformer is properly grounded and protected. Remember, grounding provides a low impedance path for fault currents, stabilizes the voltage to ground, and minimizes the risk of static electricity buildup. Always consult with a qualified professional for specific guidance on your installation. Neglecting proper grounding can have severe consequences, including electrical shock, equipment damage, and fire hazards. Therefore, it is crucial to prioritize grounding in all electrical installations. In summary, when dealing with a 240 to 120 volt 15 kVA transformer with zone and X4 secondary connections, grounding either zone or X4 to a grounding electrode system is mandatory. This practice ensures safety, facilitates the operation of overcurrent protection devices, stabilizes voltage, and mitigates static electricity risks. Refer to NEC section 250.30 for specific requirements on grounding separately derived systems like transformers, and remember to use appropriately sized grounding conductors as specified in NEC table 250.102. C1. Proper bonding of all metal enclosures and equipment, as per NEC section 250.92, is equally important. Overcurrent protection, guided by NEC table 450.3. A. Further safeguards the transformer against overload and short circuit scenarios. Adhering to these guidelines, consulting qualified professionals, and prioritizing grounding are essential steps in ensuring a safe and compliant electrical installation. The significance of grounding cannot be overstated due to the potential hazards associated with its absence. Grounding electrical systems is a fundamental safety practice. The grounding electrode system itself is a critical component. It typically consists of ground rods, ground plates, or metal underground water pipes, all interconnected to establish a common grounding point. This system must meet resistance requirements as outlined in the NEC. The grounding conductor connects the transformer's secondary winding to the grounding electrode system. The size of this conductor is determined by the size of the transformer's secondary conductors according to NEC table 250.102. C1. The connection to the grounding electrode system must be made using approved methods such as exothermic welding or listed grounding connectors. Bonding, as mentioned earlier, plays a complementary role to grounding. It involves connecting all metal parts of the electrical system to create a low impedance path for fault currents. This includes the transformer enclosure, conduit, and any other metal equipment that could become energized during a fault. NEC section 250.92 provides detailed requirements for bonding. Overcurrent protection is another essential aspect of transformer protection. Circuit breakers or fuses are used to protect the transformer from overload and short circuit conditions. The size of the overcurrent protection device should be based on the transformer's kVA rating and the secondary voltage. NEC table 450.3 provides guidance on the maximum size of overcurrent protection devices. When installing a transformer, it's crucial to adhere to all applicable electrical codes and standards. Obtain necessary permits, conduct thorough inspections, and test the installation to ensure safety and compliance. Consulting with a qualified electrical engineer or electrician is highly recommended to ensure the installation is properly designed and installed. In conclusion, grounding a 240 to 120 volt transformer is essential for safety and reliability. By adhering to the NEC requirements, implementing best practices, and seeking professional guidance, you can ensure that the transformer is properly grounded and protected. Remember, a properly grounded system minimizes shock hazards, prevents equipment damage, and reduces the risk of fire. Therefore, prioritize grounding in all electrical installations. Think of grounding as a fundamental layer of protection in your electrical system. It works silently in the background, ready to act in the event of a fault. By understanding the principles of grounding and following the code requirements, you can ensure that your electrical system is safe and reliable. Don't underestimate the importance of grounding. It's a crucial safety measure that protects people and equipment from electrical hazards. Make sure your electrical systems are properly grounded and bonded. It's a small investment that can make a big difference. Consider grounding as a way to give electricity a safe path to follow. When everything is working correctly, the grounding system remains dormant. However, the instant a fault occurs, the grounding system provides a low impedance path for the fault current to flow back to the source, tripping the overcurrent protection device and energizing the circuit. This quick action prevents the fault from escalating into a more dangerous situation.